Welcome back, everyone, to today's Explainer. I'm absolutely thrilled to dive into this with you because today we're embarking on a pretty fascinating journey into the very forces that power our universe. We're officially kicking off Unit 2 of our Physical Science series, and we're focusing specifically on energy phenomena and systems. Now, whether you're a 7th grader tackling physical science for the first time, or honestly, just a focused learner wanting to upgrade your understanding of how the world works, you are in the exact right place. We're going to break down some complex physics into crystal clear concepts, and we'll be looking at everything from tiny atoms all the way up to speeding cars. So get comfortable and let's jump right in. Right off the bat, I've got an essential question for you, and I want you to keep this in the back of your mind throughout this entire explainer. Where does energy go when systems change? It's kind of the central mystery of today's lesson. When a skateboarder stops, when a flashlight turns on, or, when a toaster heats up your morning bagel, what's actually happening behind the scenes? Energy doesn't just do things randomly. It follows some very strict, almost magical rules. And by the end of our time together today, you're going to be able to track exactly where that energy is going. So here's our game plan for cracking this mystery together. First, we'll ask, what is energy? Second, we'll look at systems and energy transfer. Third, energy models, like a flashlight and a toaster. Fourth, motion models. And finally, a quick knowledge check to see what stuck. Okay, let's dive into part 1. What is energy? Let's build up that vocabulary toolbox. First up, we've got kinetic energy. Simply put, kinetic energy is the energy of motion. Literally, anytime you see movement in the physical world, you are seeing kinetic energy in action. But I want to draw your attention to a very specific, absolutely crucial detail here. This energy grows with the square of its speed, and it's proportional to the mass of the moving object. Think about it like this. Rolling a tiny pebble down a hill, that creates a little kinetic energy. Rolling a massive boulder down that same hill, that creates a massive amount of kinetic energy. Just don't drop that boulder on your foot. And actually, here's the wild part. If that boulder rolls twice as fast, it doesn't just double in energy. It has 4 times the energy. So mass and speed, those are the 2 ingredients that make up kinetic energy. Now, what's kind of wild here is that the objects we're talking about don't necessarily have to be doing anything. Yet. And that brings us to potential energy. It's exactly what it sounds like, stored energy. It's energy just waiting for the right moment to release. Potential energy depends entirely on the relative positions within a system. Imagine holding a heavy book high above your head. Just because of its position relative to the Earth's gravity, it has gravitational potential energy. Or think of 2 strong magnets held close together, but you're physically preventing them from snapping perfectly into place. That's magnetic potential energy. Potential is there, it's just stored in the arrangement of the objects. Our third big definition is thermal energy. Now, in everyday language, we often just call this heat, but scientifically speaking, thermal energy is happening on a totally microscopic scale. It's the kinetic energy of tiny atoms and molecules vibrating and bouncing around inside a substance. The faster those microscopic particles move, the higher the thermal energy. And well, the hotter the object feels to us. If they were to stop completely, which, by the way, is basically impossible, that's what scientists call absolute zero. So temperature is really just a measure of the average kinetic energy of those particles. It's a really fantastic way to connect what we see on a large scale, like a boiling pot of water, to what's happening at the atomic level. Moving right along to Section 2, Systems and Energy Transfer. Time to learn the rules of the game. So, to really understand energy transfer, we first have to draw a boundary around what we're actually looking at. That is what a system is. A system is just a specific collection of interacting objects or components that we choose to study. By defining a system, scientists and engineers can track exactly what inputs are going in, what processes are happening, and what outputs are coming out. You could define your system as something as small as a single AA battery or as massive as the entire solar system. The key here is that we draw an imaginary box around our objects so we can watch how energy behaves inside that box and how it crosses the boundaries of that box. Now, I really want you to think about this next part. Does energy ever just disappear or get used up? It is one of the most common misconceptions in 7th grade science, and honestly, even for a lot of adults. When your phone battery dies or when a spinning top finally wobbles and stops, it certainly looks like the energy just vanished into thin air, right? It feels like the energy has been completely consumed. But is that what's actually happening according to the laws of physics? The absolute definitive answer is no way. This right here is the law of conservation of energy. So the crucial point is, energy is never lost, it simply transfers. When the motion energy of an object changes, there's inevitably some other change in energy happening at the exact same time. It moves from one object to another, or it changes from one form, like potential, into another form, like kinetic or thermal. The total change of energy in any system is always accounted for by the energy moving in or out. It's like the universe is the ultimate accountant. Literally not a single drop of energy is ever misplaced. All right, let's jump to section 3, energy models. Let's track that invisible flow. Let's see how this actually works with something simple, like a flashlight. So our system here is the flashlight itself. We start with chemical energy stored inside the battery. When you flip the switch, that chemical energy doesn't just disappear, it transfers. It becomes electrical energy flowing through the little wires. And where does that go? Well, it hits the bulb and transfers into light energy, so you can actually see in the dark, and thermal energy, which is why the bulb feels warm if you touch it. Look at that! We successfully tracked the energy from start to finish. It didn't vanish, it just changed costumes along the way. Let's try another model to make sure we've got it. This time, our system is your everyday kitchen toaster. The energy enters our system as electrical energy from the wall outlet. That electricity flows right into the wires inside the toaster, where it transfers into intense thermal energy in the heating coils, which is what toasts your bread. But wait, there's more. If you look inside a toaster while it's on, notice how those coils glow a bright orange? That means some of that thermal energy is also transferring into light energy. The energy from a power plant miles and miles away is now perfectly browning your bagel through a series of very predictable transfers. Next up, section 4, motion models. This is potential and kinetic energy in action. Imagine a skateboarder right at the top of a halfpipe, or a large hill, right at the very edge, right before they drop in. They pause for a split second. At this exact moment, they have maximum potential energy because of their height relative to the ground, but they have minimum kinetic energy because, well, they aren't moving yet. Now they drop in. As they speed down the hill, their height drops, meaning their potential energy is steadily decreasing. But where does that energy go? It transfers directly into speed, so as potential goes down, kinetic energy hits its maximum. It is a perfectly balanced seesaw of energy transfer. Now let's look at a car. A moving car speeding down the highway has massive amounts of kinetic energy. But what happens when, say, a squirrel runs into the road and the driver slams on the brakes? The car stops. The kinetic energy drops to zero. Did the energy disappear? Remember our golden rule? No. And this brilliantly illustrates exactly what happens. The brakes create friction against the wheels. That friction forces the kinetic energy to transfer completely out of the moving car system and into the environment as thermal energy. In fact, brake pads get incredibly hot, sometimes over 400 degrees. The motion energy didn't vanish. It just turned into heat and radiated away. All right, we've made it to section 5, a quick student knowledge check. Let's see what's actually sticking. Here is a challenge for you based on everything we've covered. If energy is never lost, why does a skateboarder on a perfectly flat road eventually roll to a stop? I mean, they aren't going up a hill to build potential energy, and they certainly aren't hitting the brakes like a car. They just slowly lose speed. I'll give you a second to think about the invisible transfers happening here. Well, if you guessed friction, you absolutely nailed it. The kinetic energy of those rolling wheels is constantly battling the friction of the pavement, not to mention the air resistance pushing against the skater's body. That friction is continuously transferring the skater's kinetic energy into thermal energy, slightly heating up the wheels, the road, and even the air around them, until all the kinetic energy is transferred out of the system and they come to a complete stop. So, just to wrap things up, our big takeaways today are energy transfers between kinetic, potential, and thermal states. A system is just a boundary we draw to study interacting objects. Energy is strictly conserved. It is never ever lost. It only moves in or out. And finally, by understanding these rules, we can model energy transfers in literally anything, from skateboards to toasters. I want to leave you with this final thought. Science isn't just something that happens in a textbook or a classroom. It is happening constantly all around here. Next time you use your phone, watch a bird fly, or even just see a door swing shut, ask yourself, what invisible energy transfers are happening right in front of me? Once you start looking for these systems, I promise you'll never see the world the exact same way again. Thank you so much for joining me in this explainer. Keep asking questions, and I'll catch you next time.